Hello class, I'm going to go over 4 examples of forces. Example 1, we have a box on the floor and it's being dragged by a force F. Let's say it's a rope. Okay, first step, draw all your force vectors, N, normal force, weight, and then draw your coordinate system. Make sure your forces are lined up in the Y and X direction. Here, F is at an angle, so let's draw its components, Fx and Fy. Here, let's write everything for some of the forces in the X and Y direction. So let's do X first. Some of the forces of the X equals MAX, because the box is moving along the X direction. All the forces in the X direction is just Fx. And then MA. We can rewrite Fx as force times cosine theta, because let's say we're given force and theta. Alright, now let's do some of the forces in the Y, which equals 0, because the box is not floating in the air. So we have N minus mg, which equals 0. So, common problem here you can solve for is, what is acceleration? So, you can rearrange the variables to solve for acceleration, would be a common problem in this situation. Here we're assuming that the floor is frictionless, so there's no friction in this problem. Alrighty, let's move on to the next one. Here we have a pulley system. Okay, so we draw all our forces. We have weight pointing down, and we have tension pointing up. Now for a pulley system, it's a great idea to redraw the pulley system into a straight line and redraw your force vectors as so. Then draw your coordinate system that correlates with this straight pulley system. Okay, so the pulley is moving along the X direction, is not moving along the Y. So we do some of the forces in the X direction equals MAX. Plug in all our forces in the X. We have a lot. We have negative M1G plus T1 minus T2 plus M2G equals, now we're doing the whole system here, so we're going to say M1 plus M2. So all your masses in your whole system. Ignore the dotted red lines for right now. Times AX. Then all the forces in the Y, well look, there's none in the Y, so 0 equals 0. Now, let's say we want to solve for tension, okay? But however, when we use this equation, tension cancels out. So in order to solve for tension, we have to break up our system and analyze a smaller system. So that's what we use the little red box for. And that's what this little red writing here is to represent what's in the red box. So some of the forces in the X equals MA. We have negative tension plus M2G equals all the masses in that little system, which is just M2 times AX. And here we can solve for tension. It would be a classic example. Classic example up here would be solving for A. What's acceleration? Alrighty, next problem. Here we have another pulley system, but just slightly different. Here are all our force vectors, and here we're going to assume that there's friction, let's say. Alright, now again, it's a good idea to draw this pulley system in a straight line, like so. Ignore the red dots. Here are all our force vectors, and here's our coordinate system, and this system is moving along the X direction, not Y. Some of the forces equals MA. Here are all the forces, and it equals both masses, okay? And then times AX. Tension cancels out. We can replace friction with the definition of mu, which is the coefficient, times the normal force, N. And that's it for this one. And then for some of the forces in the Y, we just have two vectors, N minus M1 times G. Now, classic problem here is we could solve for what the coefficient of static friction is, or kinetic friction, I guess it would be moving. So in order to solve for that, we have to plug in what N would be. And we can solve for N by doing some of the forces in the Y. So here N would equal M1 times G, and we would plug that in right into this equation here. And then we can solve for mu. Another classic problem is to solve for tension. To solve for tension, we have to break up our system. Here we break it up with the little red dots. And we do some of the forces in the X direction, which equals MA. So we have tension, and we have M2 times G, and that equals all the masses in that system, which is just M2 times AX. So here we can solve for what tension is. Alrighty, next problem. Last one. Let's say we have a box on a ramp. Okay? When you have a box on a ramp, it's a good idea to set your coordinate system along the same angle as the ramp. When you draw your force vectors, alright, this force vector is at an angle, so we have to draw its components, so it's along the y and x direction. Note that this angle is the same as the angle on the ramp. And here, let's assume that there's friction. Sum of the forces in the x equals ma. All our forces in the x is friction minus weight in the x direction. We can rewrite friction as the definition of mu times normal force, minus, and we can rewrite Wx as mg times sine theta, all equals max. Then for the y, we have two components, normal force and the weight in the y direction. We can rewrite weight in the y direction as mg cosine theta. Classic problem here would be solving for either acceleration, or let's say we could solve for the coefficient of kinetic friction. But to solve for the coefficient, we have to plug in what the normal force is, and to get the normal force, we get that down over here when we solve for components in the y direction. So the normal force would equal mg cosine theta. So you'd plug that right into there. And that is it for this screencast. Have a good night.